In this video, we want to talk about Taylor polynomials, specifically about inventing Taylor polynomials. And what I mean by that is, if we didn't know that such a thing existed, and we wanted to have some way of emulating some function, perhaps some very complex function, then we would need to invent a method of doing that, of emulating this function. And that's what we're going to do in this video. We're going to start at 0 and say, I want to emulate some other function using a polynomial. How would I go about having this idea? That is, we want to reinvent Taylor polynomials. So let's say we had some function. Let's say the graph of this function looks something like this. We'll call that function f. And I want to invent some polynomial p, in other words, a polynomial function that emulates this function. So where do I begin? Well, it's hard to think of an idea of just saying I want p to be like f in some abstract way. We need to start somehow concretely, and let's just say we pick some point. Maybe the point that we pick is this one here. We just pick some point, and we'll call that point A. And let's start at that point and see if we can basically copy this function f. So the first characteristic that we would want to have to be the case for p, would be that p of a should at least be equal to f of a. Right? So we don't know what our function p is going to look like. Maybe it will look like this, or maybe it will look like this. Maybe it won't be a perfect copy. But in any case, we do want this point to be the same. So let's take a first stab at that. Let's just say that I'll write that here. First try. Our first try is just going to define the polynomial function to be f of a. In other words, we're just going to have this constant function. That's the first try. So that perhaps is not such a great, actually, yeah, let's make that red so that all of our approximations will be in a different color so we can see them. That's our first try. Not such a great try, but we see that it does emulate the function a bit. At least it shares the point at A. Now, the next question is, what could we do from here? Well, one idea we might have is to say, well, let's just go to the next point. We'll call that maybe point B. And we'll say that we also want p of b to be equal to f of b. But the question here that we would have to answer and would not be able to answer would be, well, what is the next point after a? Let's say a is equal to 3. Well, what would b equal to? Is 3.1 or 3.01 or 3.001, right? There is no next point. So that line of thinking is not going to get us anywhere. The idea, the good idea, that we're going to need to have is that perhaps our polynomial function could just have the same, not only the same function value at a, but the same slope at a. So in other words, we want p prime of a to be equal to f prime of a. Now, how would we go about that? Well, let's, as a first sort of stab at it, let's just add this first derivative, or this value of the first derivative, right there. So what do we get if we evaluate p of a? We get f of a, which is good because that's what we wanted, but of course we also get f prime of a, which we didn't want. F prime, the slope at this point is not equal to 0, so that's just going to to screw up our first value, right? So this is not going to be equal to f of a anymore, which is what we wanted. So we're going to have to come up with some sort of way of, we know that this f prime has to play a role somewhere, so it has to be there. Otherwise we can't get this slope to be the same. But we also know that it can't play a role when we're doing p of a. So here we also need a good idea, and that good idea is to multiply this times x minus a. So that means, actually let's go back and change this in the definition here. So we would change this to be f prime of a times x minus a. So that way when we take p of a, we end up with f of a plus, and now if we sub in an a for this x, this goes to 0. So f prime of a times 0, which just gives us f of a. So that works out well. Now let's see what that would mean for us as far as f prime of a. Well, first we need to figure out what f prime of x would be equal to. So let's take the derivative of this. F of a is just some constant, right? Since this is not an x in here, it's just an a. So f of a is just some value that goes to 0. And the derivative of this, since again this a is just a constant, would be f prime of a, which gives us altogether f prime of a, which is exactly what we wanted. Because now if we take p prime of a, we get f prime of a, which was the second characteristic that we wanted to have. So this is going well. The next approximation would maybe look something like that, right? That would have the same slope here at this point a. So let's continue now, and actually let's label that. We'll say that this is our second try. This is our second try right here. Second try. So let's look at our third try now. We're going to want to have the third derivative, the second derivative be the same. So that would give us something like this. We'll just take a stab at this. It would be f of a plus, we'll keep initially the same thing we had before. And here we don't know exactly what we need, but it must be something similar, right? So we'd have f double prime of a, and again we'll use our trick with x minus a. So what would be the, well actually let's just evaluate that. So p of a would be f of a plus, now this is going to fall away, and this is going to fall away when we sub in a for x, so that's just 0 plus 0, and that gives us f of a. Great. So far so good. Now we need the first derivative of p, so we're going to just take the derivative of this here. So again, this will fall away, that becomes 0. This would just be the derivative of this is f prime of a plus, now the derivative of this would be f double prime of a, which is going to cause a problem, right? Because now when we evaluate p prime of a, we're going to get f prime of a plus f double prime of a, right? This is going to be in the way here. What is this doing here? So it turns out we're going to have to add a power here in order to keep this x minus a around for a bit longer, because that means the first derivative would be this here, right? We would just take this 2 down, taking the derivative, and have an x minus a here, which means when we evaluate that at a, that since we still have this x minus a hanging around, that this again would be a 0, and we would end up with f prime of a. Perfect, that's just like we needed it. So now we'll take the second derivative of p. So in other words, we're taking the derivative of this here. 0 plus, now again this is just a constant, so that's 0. And we end up with, the derivative of this would be 2f prime of a. Now what we really needed to have for our simulation would be p double prime of a being equal to f double prime of a. Right? That would be the third characteristic that we would want our simulation to have. But we're having a 2 here, so that's a problem. So we're going to have to go back to our original stab at this and divide this whole thing here by 2, which would get rid of this 2 and give us exactly what we want. So that was our third try. Each time we're adding one more degree to our polynomial. That's our third try. And so with this knowledge, we can do a fourth try. I think once we see this fourth try, we'll see the pattern. Actually, let's take a look at what that new try would look like. If the second degree is the same, then maybe the graph would look something like this now. Right? So it's getting closer. It's still not the same, but it's getting closer. For a little bit more of a stretch, it shares the same values. Okay, so our fourth try, we would then want to have p triple prime of a being equal to f triple prime of a. So let's just continue our pattern that we had before. We would have f of a plus f prime of a times x minus a, because we want this x minus a to hang around a little bit. And then we had f double prime of a times x minus a squared, because we want this x minus a to hang around a little bit longer. We divided that by 2. And then we had f triple prime of a. Well, we didn't have that, but that's probably what we would expect. And we would probably expect this to be a 3. And then we would probably be dividing by something, but we don't know exactly what, because here we didn't have to divide by anything. Here we didn't have to divide by anything, and then here we suddenly had to divide by 2. So let's figure out what would be needing to divide by here. So in other words, let's take the different derivatives of this term here. So we have this term in our original p here. So the first derivative would be, now don't forget that this is just a constant, right? This f triple prime of a is just a constant. We don't need to do anything with that. So the first derivative would be 3 f triple prime of a times x minus a squared. The second derivative would be, this 2 has to come down, so that would be 6 f triple prime of a times x minus a. And the third derivative, which is what we're interested in, would be 6 f triple prime of a. In other words, it's 6 times higher than what we actually want. So we're going to need to divide this by 6. So now we've done 4 terms, gone up to degree 3. Let's see if we can find a pattern so that we can continue this without having to figure out each successive improvement. And while we're at it, we can look and see what this new improvement would have brought. Maybe the new improvement would be something like this. Again, just a somewhat better simulation of the function f than before. So now let's look, see if we see a pattern. We divided here by 6, we divided here by 2, and here we didn't divide by anything at all. But of course we could also just say that what we were doing is dividing by 1. And here we also divided by 1. and here we divided by 2, and here we divided by 6. Now here we don't necessarily need a great creative idea, but a good sharp eye, and to see what sort of pattern that is. It turns out that 6 is just 3 factorial, 2 is 2 factorial, 1 is 1 factorial, and 1 is also 0 factorial. That definition of 0 factorial being equal to 1 helps us, in this case, find a nice pattern. So, let's look for some more patterns. Here we have a 3 and another 3 for this 3 factorial. And we also have 3 apostrophes. So in other words, we're taking the third derivative. Here we have 2 factorial, we have the power of 2, and also 2 apostrophes. The same goes for here. We have 1 factorial, 1 apostrophe. We don't have a 1 here, but we could go ahead and just write that that's the first power, right? So we could write that 1. And then we can get back to this one here. We do not have, oh, I guess we do have 0 apostrophes, right? We have 0 apostrophes, so that works. But we don't have this term here. We could go ahead and write it though. We could add an x minus a here just to the 0th power, right? So since that's 1, that works out. And instead of these apostrophes, we could just write a different notation here. We have 0 apostrophes. Here we have 1 apostrophe. So in other words, the first derivative, this is the second derivative, and this is the third derivative. So again, this definition is just that the number written in parentheses tells us which derivative that is. And if we write it in this way, and if we generalize and just call this k, all these numbers here, then we would have the kth derivative of f evaluated at a times x minus a to the kth power, and we're dividing that by k factorial. So in other words, if we define our function this way, it's just a sum of all of these up to some degree. Let's just call it n, let's say. So in other words, the highest degree that we're going to be using in our simulation we'll call n. Then we would have this as our simulation of f. And let's give that a more complete name. What did this simulation depend on? Well, it depended on this point A that we had to choose. So let's include that in the name. And it depended also on which degree of the polynomial that we ended up going to. So let's call that n and a. So p sub na of x is equal to the sum from k equals 0 to n of the kth derivative of f evaluated at a divided by k factorial times x minus a to the kth power. And you see that each one of these derivatives got better and better. So let's just take a look at, very quickly, an example. So if I had, for example, the exponential function, and I wanted to use our idea now of inventing a polynomial to simulate that, then the very first polynomial that I would come up with turns out to be this, and you see that this is the simulation here. Now how did I come up with this 1? Well, we know that the very first value is just equal to, we said before, f of a, and it turns out in this case, if this is our f, that's just the exponential function of, what point is it that we're looking at here? It's 0. So the exponential function of 0 is equal to 1. In other words, e to the 0th power is equal to 1. So that's how we came up with that. This approximation is not so great, but it does at least get the point right at our point A, which is equal to 0. The second improvement, or the next improvement, would be this here. Just as we saw before, this slope is the same. This would be the next improvement, and you see the red curve is getting closer to the blue one. This would be the next improvement. This the next improvement, and here, when we've reached the 5th degree, you already see that at least for this small stretch, our simulation almost exactly emulates the original function. So that is how one might go about inventing Taylor polynomials if they didn't already exist.